This is Honors Geometry Chapter 3 Proofs video. Here's our first one. Step 1, of course, is given. Step 2, why is measure of 2 equal measure of 1, 3 equal 4, 6 equals 5, and 7 equals 8? That's because as we look at all these parallel lines that we have and the transversals, we know that parallel implies that those corresponding angles are equal to each other. Then why does 6 equal 7? Well, if we look at the path, 6 equals 5, and the given 5 equals 8, 8 equals 7, so this would be a transitive. Number 4, we're taking 6 equals 7 and we're converting it into congruent. That is the definition of congruent angles. Step number 5, now if we look back at the drawing, 2 and 6 are supplements, 3 and 7 are supplements. That would be the linear pair postulate. Number 6, this is a seldom used reason, but since 6 and 7 are congruent to each other, 2 is supplementary to 6, 3 is supplementary to 7, then using the congruent supplements theorem, which says that if two angles are supplementary to the same angle or to congruent angles, the angles are congruent. So that's why 2 is congruent to 3. And then we're going to convert back to equal using the definition of congruent angles. Proof number 2, we have R is parallel to S, and then we have a few different transversals. Given that measure of 1 is equal to measure of 4, we're trying to prove that angle 5 is congruent to angle 7. So once again, step 1 is given. Step 2, 5 and 1 are supplements, 7 and 4 are supplements. That would be because parallel implies that same side interior angles are supplementary. Next, we're going to convert 1 equal 4 into angle 1 is congruent to angle 4. That is our definition of congruent angles. And then using the same reason we used earlier, since 1 and 4 are congruent to each other, 5 and 7 are supplementary to those congruent angles, then using the congruent supplements theorem again, you can say that these two angles are congruent to each other. This is definitely not the only way to do this one. We could have used the definition of supplements with a transitive getting into 180, but this would be the shortest way we could do this one. All right, our next proof. We're given that F is parallel to G, and that the measure of angle 3 is equal to the measure of angle 4. So step 1 is given. Step 2, why does the measure of angle 1 equal measure of angle 3? Well, as I look at those two parallel lines in the transversal, I know that parallel implies that alternate exterior angles are equal. And then since 1 equals 3, 3 equals 4, we can get from 1 equaling 4, that would be a transitive. So we're using a lot of the given so far. We're trying to bring angle 5 into the proof. Angle 1 we have a lot of stuff with. Next, F is parallel to H. Why would that be? Well, since we now have 1 equal to 4, and since those are corresponding angles that are equal, then that means that the lines must be parallel. F would be parallel to H. Now that we have F, transversal, H, parallel to each other, we can say that measure 5 equals measure 1. Since parallel implies alternate exterior are equal, and then converting from equal to congruent, we have definition of congruent angles. This is one way we could do it. Once we had 1 equal to 4, we could have used vertical angles in a transitive, but either way would be fine. And here's our number 4. It's a pretty short proof. Step 1 is given, and we're going to start using the given since 1 is supplementary to 2, and as I look at their locations, we could say that A and B are parallel, since same side interior supplement means the lines are parallel. Also in the given, we're told that 3 equals 4, and since those corresponding angles are equal, we know that the lines are parallel. Specifically, B is parallel to C. A is parallel to B, B is parallel to C. Therefore, using the dual parallel theorem, which is kind of like the transitive property for parallel lines, we can say A is parallel to C, and that's what we're trying to prove. Number 5, we're trying to get that the measure of angle 1 equals measure of angle 3. You can work your way backwards on that one and try to think, all right, if they're equal to each other, that means that the lines would have been parallel, and then try to connect it with other things. We use a lot of the strategies we've talked about before, namely using the given. Since 4 and 5 are supplements, looking at their location, that means that we could say that I and K are parallel to each other. That would be because of SI, SP. Since 4 is equal to 6, looking at their locations, since those alternate exterior are equal, it means the lines are parallel. K is parallel to D. Step number 4, I is parallel to K, D is parallel to K. So using the dual parallel theorem, can say I is parallel to D. And now as we look over at this other transversal, since the top line is parallel to the bottom line with this transversal down the middle, then we know 1 equals 3. That would be because parallel implies that corresponding angles are equal. All right, proof number 6. We will claim the given. And then as we look at the given, we're told that H is parallel to W. So since those two lines are parallel to each other, we can say that 2 is equal to 12, since parallel implies that alternate interior angles are equal to each other. And we're also told that L is parallel to M, which means that 4 is equal to 6. Parallel implies that corresponding angles are equal to each other. So we're using both of those parts of the given. We're trying to get that K is parallel to L, so we want to get some kind of connection between this line, and one of the transversals. Now, as we're tying everything together from the given and what we've written, let's see, we have 2 is equal to 12, 12 equals 6, 6 equals 4, so 2 equals 4. That would be by a transitive. The reason why that is significant is because as we look at the location of angle 2, the location of angle 4, and consider this transversal, we see that these are corresponding angles that are equal. In other words, since those corresponding angles are equal, line K is parallel to line L. Here's number 7. Once again, first reason is going to be the given. Step 2. Since the measure of angle 2 is equal to the measure of angle 4, I can see then that those two lines, I and K, are going to be parallel. Since the corresponding angle is equal, means the line's parallel. Using that part of the given. It says 1 is supplementary to 5, and they're nowhere near each other, so that makes it a little difficult for me. Let's see how we can bring this together. All right, so parallel, transversal. Parallel means 1 is going to be equal to 6, so I'm moving down here to the bottom. That reason is going to be parallel implies alternate exterior are equal. And then let's see. 1 is supplementary to 5. 1 equals 6, so we can plug 6 in for 1. In other words, we can use a substitution of steps 3 and 1. I'm changing this statement, plugging 6 in for 1. And now as I look at their location, since 6 is supplementary to 5, and since those same side interior angles are supplementary, it means the lines are parallel. And here is our final proof, proof number 8. And this is a really tough one. I have it written down as 14 steps, and I don't know if it can be done much shorter than this. So let's just jump right into it. Step 1 given. Step 2, K and L are parallel. M and L are parallel. So K is parallel to M. That is our dual parallel theorem. Step number 3, now that I know that they are parallel to each other, angle EDA and angle BAD, these two angles here are going to be supplements because parallel implies same side interior angles are supplements. Number 4, because of our angle bisectors going back up to the given, that means that measure of angle 2 equals measure of 3. Down here, 6 equals 7. That is the definition of angle bisector. Number 5, 2 plus 3 makes up EDA. 6 plus 7 equals BAD. That is our angle addition postulate. And some of these steps and reasons are really hard to come by. So this is definitely a hard proof. We've used the given for everything we can, trying to get to the proof statement. And there's no obvious thing there. So if this is a perpendicular, it means a right angle. It means it's 90 degrees. That means that 3, 6, and 11 in the triangle would have to add up to 180 with it. So I'm going to see if I can get somehow 3 plus 6 equal to 90 degrees. And that's what I'm going after here. Let's see, going further. Since in step 3 I said these angles were supplements, now down here in step number 6 I'm saying they add up to 180. That is a definition of supplements. Number 7, this is a substitution. Instead of EDA, I'm plugging 2 plus 3 in for it. Instead of BAD, since it's equal right here, I'm plugging 6 plus 7 in for it. So that is a substitution of step 6, where we got the equation, 5, where we got the facts from. And then step 8, since 2 is equal to 3, I plug 3 in for 2. And since 7 was equal to 6, up here in step number 4, I can plug 6 in for 7. So this is another substitution of steps 7 and 4. And then angle 3 plus angle 3 is 2 angle 3. Angle 6 plus angle 6 is 2 angle 6. We would just say that simplifies using properties from algebra to simplify it. Going from 9 to 10, I notice that each one of these 3 terms can be divided by 2. we're just using division. We're dividing by 2, so I don't need to say 2 equals 2. Takes us all the way down to step 10. 3 plus 6 equals 90 degrees. That's one of the things I was looking for because 3 plus 6 plus 11, they make up a triangle. So we call this the triangle angle sum theorem. The three angles in a triangle add up to 180 degrees. So then now in step number 12, if we take step 11 minus step 10, the 3's cancel out, the 6's cancel out, we're left with measure of angle 11, and on the right, 180 minus 90 is 90. So this is a subtraction step of steps 11 and 10. And if angle 11 equals 90 degrees, that means it's a right angle. That is our definition of a right angle. And if angle 11 is a right angle, and I look back on my diagram, that means that segment FD, this segment, must be perpendicular to segment AC, that one. That is our definition of perpendicular. And that's what we're trying to prove.